In this chapter, we'll discuss energy. So looking at the definition of energy, right, we're looking at the capacity to do work. And so the ultimate source of energy in living organisms is the sun through photosynthesis. So we consume either animals who have consumed plants or the plants directly. And the body uses these energy from carbohydrates, proteins, fats, and alcohol in food. Now, at the end of the day, body weight is our indicator of energy adequacy or inadequacy. And we'll take a look at this energy balance equation, and there's some things that can be manipulated, kind of. But at the end of the day, we know if you're getting enough calories based on weight. So looking at energy requirements, so the definition, we have the dietary energy intake that is required for growth or maintenance in a person of a defined age, gender, weight, height, and level of physical activity. Now, injury or illness may increase energy expenditure, so recovery, fevers, etc. And again, body weight is our indicator for energy adequacy or inadequacy, but is not an indicator for macro or micronutrient adequacy. So it doesn't tell us if we're getting enough protein, it doesn't tell us if we're getting enough vitamin B, it just tells us if we're getting enough calories. So again, you can get enough calories and not have optimal health and be missing nutrients, but it's still the adequate number of calories. So looking at our energy expenditure, so three components make up an individual's daily total energy expenditure, or TEE. We have basal energy expenditure, the thermic effect of food, and activity thermogenesis, or physical activity. And technically there's some other pieces in here, so we can look at non-exercise activity thermogenesis, which is like a subcategory. So it doesn't include like organized exercise, but again what we're looking at is homeostasis, food breakdown, and then moving around. Now there's technically two different definitions, and you just have to be real careful when looking at literature. Again, it's not good or bad, we just want to make sure that we know what we're reading. So we have a resting energy expenditure, or resting metabolic rate. And this is energy expended in activities necessary to sustain normal body functions and homeostasis. And so resting energy expenditure is now used more commonly than basal energy expenditure. And so when we think of resting metabolic rate, this is more of like you chilling on the couch. And then basal energy expenditure, or basal metabolic rate, is the minimum amount of energy expended that is compatible with life. And this is the energy needed to keep the body alive at complete rest. It's about 10 to 20% less than resting energy expenditure. So basal is like borderline coma, laying in bed doing nothing. Resting is like you're sitting on the couch doing nothing, but your eyeballs are moving, your brain is thinking, like, you know, it's a tiny bit more involved. So factors that affect our resting energy expenditure, so age. So resting energy expenditure decreases as age increases. Body composition, as fat-free mass or lean body mass increases resting energy expenditure. Body size plays a small role, with larger individuals generally having higher metabolic rates than smaller, and taller having higher metabolic rates than shorter. And that has to do with surface area and the maintenance of body temperature. So again, if somebody has more surface area exposed to the elements, they're going to be giving off more heat, and they need to use a tiny bit more energy to maintain their body temperature. Looking at climate, resting energy expenditure is 5 to 20% higher in tropical climates. Now, so is the secret to getting skinny living somewhere hot? Well, it's more complicated than that, of course, right? You would have to actually live outside in the elements. Again, your metabolism is higher if you need to maintain your body temperature and cool off your body. If you live in a tropical or a subtropical climate like we live in, and you just get air conditioning all day, that does not affect your metabolism. Looking at gender, resting energy expenditure is 5 to 10% lower in women than men, and this is usually accounted for by a difference in total lean body mass. Hormonal status may increase or decrease resting energy expenditure. This is the infamous thyroid. Looking at temperature, fevers increase resting energy expenditure by 7% for each degree above 98.6. And caffeine nicotine, and alcohol can all increase metabolic rate. So first we'll talk about the thermic effect of food. This is the increase in energy expenditure associated with the consumption, digestion, and absorption of food, and accounts for approximately 10% of the total energy expenditure. Now it can go up or down slightly depending on the macronutrients ingested. The thermic effect of food increases directly after food intake and then decreases after the ingestion over 30 to 90 minute period. So when you first digest food, there's a huge spike in energy breakdown, and as the food gets more and more broken down, the energy expenditure decreases and tapers off. Now, the actual measurement of the thermic effect of food is really only appropriate for research purposes. We just want to make sure that, again, we're accounting for all of these sources of energy in our models. Looking at activity thermogenesis. So this is the energy expended during sports or fitness, exercise, organized activities. We also have non-exercise activity thermogenesis, NEAT, which is defined as the energy expended during activities of daily living. This is walking around, going up the stairs, parking further away from the grocery store, tapping your foot, pacing when you're on the phone, etc. Now, individual activity thermogenesis varies considerably, and activity thermogenesis tends to decrease with age, and on average, men have higher activity thermogenesis. Now, we'll also talk briefly about excess post-exercise oxygen consumption, or EPOC. And so this is based on the duration and magnitude of physical activity. We'll see an increase in EPOC, which is after you've worked out really hard, you continue to breathe heavily after the exercise. Now, you have to realize that in essence, the human body is kind of like a fire. With additional oxygen, it will continue to burn hotter and burn more calories. So after intense training sessions, you will see an increase in metabolic rate even after the exercise has ceased. And this concept is kind of how Orange Theory Fitness built its model, which is looking at by exercising at a certain intensity, you will increase EPOC. So let's take a look at how we measure energy expenditure. So here in the US, the calorie is the standard unit for measuring energy. And so 1 calorie is the amount of energy required to raise the temperature of 1 milliliter of water that started at 15 degrees Celsius by 1 degree Celsius. Now the problem is that if we were to do this, you would see hundreds of thousands of calories on your foods and you would panic. So we actually use kilocalories, or calories with a capital C, which is actually 1,000 calories. This allows us to, in essence, just cut 3 zeros off the end of the numbers and put a lot more manageable numbers on our food labels. Now you will see in many European and Asian countries, they will actually list energy in kilojoules. So 1 calorie is equal to 4.184 kilojoules. And so you may see some labels, if they're marketed in both regions, that they'll have both listed, or you may see occasionally if you get imported food items, they have had a sticker placed over the old food label to then be compliant with US standards and list calories. Now, how do we assess this? So we do have direct calorimetry. So this involves a specific metabolic chamber that's used to measure the amount of heat given off of subjects through their body, through evaporation, convection, and radiation. So we're accounting for all the different sources of heat energy. This does require, though, a whole room calorimeter. I believe that Advent Health's Metabolic Testing Center has 2 of these. I want to say it's 2. So these have limited use. They're extremely expensive, very complex. I've never even been, I've attended 3 or 4 universities. No one has one of these. We do indirect calorimetry, which we'll discuss. But these are very expensive, very scarce, and this is some very high cost research. What you'll most often see is indirect calorimetry. And so this is a measurement of oxygen consumption and CO2 expenditure over a given period of time. Now the equipment is portable, so again this is what's called a metabolic cart. So this is a mouthpiece, nose clip, mask, and a hood, along with, it's about the size of an old desktop computer, and that's the actual That's where the actual O2 and CO2 sensors are. And so metabolic carts are used in hospital ICUs and considered the gold standard for critically ill patients. So I do know they do this at Moffitt on some of their more severely sick patients. Now to do this right, we need a minimum of a 5-hour fast, preferably longer. We want to avoid caffeine, alcohol, smoking, and exercise prior to measurement. As we discussed on the previous slides, those would all increase metabolic rate artificially. Now here you can see, and so the technology has come a long way, but I don't make the licensing, but you can see, so this is the hood, and again you can see the machine, although now they are much smaller. Like I said, they're about the size of an old desktop computer. And again, so you'll see this, in this case, this one has a hood. The other option though is a mouthpiece and nose clip, which is what we have on campus. So here you can see a little bit more modern version. Again, you can see the size of the device has significantly decreased. And again, this is the hooded version, but we actually use a mouthpiece. Now, if a patient is in the ICU and on a breathing machine, the hose and the tubing can actually be directly connected to the patient's breathing machine, and you would not see any hood over the patient. Now, all of this relates to, and the reason why this is so important is that from a clinical standpoint, we're very worried about respiratory quotient. And so this is the body's total exchange of oxygen for CO2, expressed as the ratio of volume of CO2 compared to the volume of oxygen consumed per unit of time. Now the values of the respiratory quotient change based on the fuel source or macronutrient being burned. And the ratio ranges from 0.7 to 1.0. Now the theoretical 1.0 would be pure carbohydrates. Pure fat is represented by 0.7, with a mixed diet being exactly in the middle at 0.85, and pure protein at 0.82, although this is mostly theoretical as the body should not be burning protein for its primary energy source. Now you can see lower values, so less than or equal to 0.65, if the body is using ketones primarily as an energy source. Other ways to assess this, we can use what's known as doubly labeled water. So this is the gold standard for actually measuring total energy expenditure. And this is based on the principle that CO2 production can be estimated from the difference in the elimination rates of hydrogen and oxygen. And so over a 10 to 14 day period of time, subjects drink 2 different isotopic forms of water, and urine samples are used to measure the rate at which these isotopes disappear from the body, and this allows us to calculate energy expenditure. So again, through the breakdown and excretion, we can then see how fast your body is breaking things down, which is what's telling us your metabolism. So the doubly labeled water method is accurate within 2 to 8% precision. So administration is easy and individuals are able to engage in their activities of daily living. And this is most applicable as a research tool to help validate predictive equations for estimating energy requirements. So again, you've seen the Mifflin-St. Jeor, which we've discussed, right? These equations to calculate energy needs. This is how we confirm the equations are accurate. Now the only problem is that these stable isotopes are expensive and expertise is required to operate the mass spectrometer and actually calculate the results. Now again, we've discussed, so we have our equations for estimating, so these are just estimating our resting energy expenditure. And the Harris-Benedict equation is the most famous one. So it was most widely used until recently, and I say recently is as in the last couple decades. This was established in 1919 and found to be overestimating resting energy expenditure in normal weight and obese. And that's because the Harris-Benedict equation was calculated using military personnel, and so that patient population was a little more fit than the average person, and so this artificially increased the calories for the equation. We now use the Mifflin-St. Jeor equation, which is established in 1990. This is found to be more accurate in estimating resting energy expenditure in healthy weight and obese individuals and has been validated in many studies. Additionally, Dr. St. Jeor continues to refine her equation, and so what they actually do is that based on compiling data from large sample sizes and looking at multiple studies, they continue to edit and refine the equation. So here you can see as a review the Mifflin-St. Jeor equation. And so again, you'll actually see in the literature, so the actual equation started with 9.99 for weight. This was changed to 10 as they found through their trial and error and validation studies that it didn't really make a difference, but it makes it much easier for calculation. So we have our weight in kilograms, our height in centimeters, age is in years. Thank goodness there isn't a metric system for years. And then again, a correction factor for males and females. And in essence, what you see is at the end of the day, there's only about 166 calorie difference between males and females. Now, the one thing I will note is you will also need to use an activity and/or injury factor depending on the patient's condition, and do not use adjusted body weight. You need to use actual body weight, what the person actually weighs, for this equation to be most accurate. Now here you can see the activity factors. So again, even if you're bedbound, people move around in bed. Not a whole lot, but they move around. So the activity factor is 1.2. Or if they are ambulatory, which is just saying this is not physical activity, this is I can get up and walk to the kitchen and grab a snack. I can walk to the bathroom, etc. I can just do some basic walking around. Here we have our injury factors. So based on how injured or sick the person is with minor or major surgery, mild to severe infection, skeletal trauma, head injuries, or burn surface area, we would then further increase calories. So you take the equation's results and multiply it by these numbers. Here you can see the Harris-Benedict equation. Although you really shouldn't be using it too much in practice, again, I just want you to see it. I would have it just in case if you have a preceptor that chooses to use it. I would rather over-prepare you than under-prepare you. So looking at estimating energy requirement from energy intake. So again, our EER is the average dietary energy intake that is predicted to maintain energy balance in a healthy adult of a defined age, gender, weight, height, and level of physical activity. And so this is developed by the Institutes of Medicine, the Food and Nutrition Board, and the National Academy of Sciences. And the equations utilize the physical activity levels. So again, there's a predetermined category of physical activity that patients would be estimated to engage in. So, based on a number of total minutes per week. Now, estimated energy expended in physical activity. So there is an appendix in the back of your text that discusses METs, which tells us an activity and calories, or what we can do is we can then use METs and apply this to any body weight. So what is a MET? So a MET is a metabolic equivalent. And so these are a unit of measure that corresponds with a person's metabolic rate during selected physical activities at varying intensities. So 1 MET is 1 calorie per kilogram per hour. So for example, a 65 kilogram person doing nothing, a 65 kilogram person doing nothing burns 65 calories per hour. What we then see is that there is what's known as a MET table from old studies, and this tells us that walking moderately at 4 miles per hour has a MET value of 4.5. What this tells us is the patient is burning 4.5 times more calories than doing nothing. So you then multiply 4.5 times body weight times the amount of time that the activity is performed. So if I sit on my butt and do nothing, I would burn 65 calories. If I exercise at 4 miles per hour, my metabolism is 4.5 times higher, and I would burn 4.5 times 65. I would burn 293 calories by exercising instead of the 65 from just sitting still. Now calculating food energy. So this is done using a bomb calorimeter, and this is used to measure the total energy available from food. Now that being said, the processes of digestion and absorption are not 100% efficient, so not all of the energy contained in foods and alcohol is available to the human body. Therefore, the biologically available energy from foods and alcohol is expressed in values that are rounded off slightly below those that are obtained from using the bomb calorimeter, so in the lab results. So here you can see we have our gross energy of food, which is the heat combustion. So you'll see these numbers are larger. Then we have our digestible energy, and then we have our metabolizable energy. And so what you'll see this process of decreasing efficiency. So protein actually contains 5.65 calories per gram on average, but we as humans can only access about 4. Carbohydrates, you will see, contain slightly more at 4.1, but we can only on average metabolize 4.0, and so on and so forth. Now again, I'm sure you've seen this, which is calculating food energy, as many foods contain a mixture of protein, fat, carbohydrate, and alcohol, so we can do this based on the composition of the food. For example, a medium egg is 50 grams, and by weight is 13% protein, 12% fat, and 1% carbohydrate. So 13% times 50 grams tells us there is 6.5 grams of protein in the egg. At 4 calories per gram, that tells us there is 26 calories. We do this again for protein at 12%. This tells us there is 6 grams of fat in the egg. At 9 calories per gram, this is 54 calories from fat. And at 1% from carbohydrate times 50 grams, this gives us 0.05 grams of carbohydrate at 4 calories per gram, giving us 2 calories. We add these up and you'll see there is 82 calories. So this is why you'll see that eggs are commonly rounded and listed as 80 calories. This is also the same information that you will see on the back of a food label. Now looking at alcohol, so the way we can calculate the calories in alcohol is the amount of the beverage in ounces times the proof times 0.8 calories per proof per 1 ounce. So for example, how many calories are there in 1.5 ounces of 86 proof whiskey? We would take 1.5 times 86 times 0.8 tells us that there is 103 calories in a shot of approximately in a shot of 86 proof whiskey. Now again, just as a reminder, to determine the percent ethyl alcohol in a beverage, you divide the proof by 2. So an 86 proof whiskey is 43% ethyl alcohol. Now remember, this was important when they were discussing how to make hand sanitizer, in that 80 proof whiskey, right, or 80 proof vodka, as Tito's was the brand that had to put out this information, cannot be used to make hand sanitizer, as it does not contain enough alcohol. So let's take a look at some review questions. So the factor that has the greatest effect on basal energy expenditure. And this is C, fat-free mass. Number 2, the respective number of kilocalories in a gram of protein, carbohydrate, and fat is, and this is 4 calories in 1 gram of protein, 4 calories in 1 gram of carbohydrate, and 9 calories in 1 gram of fat. The effect of caffeine, nicotine, and alcohol on metabolic rate is as, and this is answer choice A, stimulants. These substances increase metabolic rate. And number 4, the thermic effect of food is the, and this is D, increase in energy expenditure associated with digestion, absorption, and metabolism of food. Thank you, and I look forward to your questions.